Alright, hello everyone. Welcome to the MATH2621, MATH2521 revision seminar. So in terms of topics, there are 4 topics, right? So introduction to complex analysis, limits and differentiability, series and Fourier and Laplace transforms. So I will be doing introduction to complex analysis, and then for the rest of today, Marcus will be taking over limits and differentiability. So to get started, we're going to look at a sort of brief introduction to complex analysis to revise some of the fundamentals. So some basic rules and ideas. So our very first basic object is the complex number itself, right? We should know that it has 2 representations. So we have a Cartesian form, right? Which is like z equals x plus iy. And we also have an Euler form, z equals r e to the I theta. And so we should know that normal rules of addition, multiplication, subtraction hold. And division's a little bit weirder. We'd have to multiply by conjugate if we're doing it in Cartesian form, but we should have seen that before. And then our last basic idea is that geometrically, multiplying complex numbers involves scaling and rotation, okay? And that comes from the Euler form, right? We know that if I have, let's say like r1 e to the I theta 1 times r2 e to the I theta 2, we should know that we multiply those moduli and then we add the arguments inside, and that corresponds to our geometric interpretation. Okay, and some important ideas here. Well, this is one important identity. So to get the modulus squared, we multiply a complex number with its conjugate, and then principal argument. So remember that complex numbers could have infinitely many arguments because we can keep adding 2 pi. Okay, so our principal argument is the argument that lies in the range negative pi not inclusive to positive pi inclusive. Okay, so we're going to get started with looking at some inequalities and sets. Okay, so our first major inequality is the triangle inequality. Okay, and our second major inequality is the circle inequality. So you want to know these inequalities really well because they can help you, and we're going to see some questions where they're useful very soon. Okay, so in terms of Math2621, we will learn a little bit of basic topology and sets. Okay, so the very first object that we're going to be looking at is something called the ball inside our complex plane. So the open ball is the set of all complex numbers that satisfy this. Okay, so it's an open ball at center z0 and radius epsilon. And again, we can just think about it as just a circle inside the complex plane. So if we had a point z0 like here, we can see that this open ball is literally just going to be the circle surrounding z0 with radius epsilon, including all the points inside the ball, okay, but not including the boundary, okay, so not including this actual circle itself, okay. So we include all the points inside, but we don't include the boundary itself. That's why it's called an open ball. All right, so there are certain types of points inside like sets, okay? And these points that are important to us are interior points, exterior points, and boundary points. So if we look at the definition of an interior point, it says there exists an epsilon greater than 0 such that the open ball centered at x with radius epsilon is entirely contained within the set. So to look at an example, right, we could have some arbitrary set that looks like this. Okay, let's say just some arbitrary set like that. And then we can look at a point x. So we can visually say that this lies in the interior, but how can we say that mathematically? We can say because there exists some open ball surrounding x, right, with radius epsilon, so that the open ball is entirely contained within the set, okay? So now, exterior point, so there exists an epsilon greater than 0 so that the intersection between this open ball and the actual set itself is the empty set. So for example, if we looked at a point over here, okay, there exists some open ball with radius epsilon, so that if we look at the intersection between this open ball, okay, and the actual set S itself, then clearly we get the empty set because there's no overlap there. And then finally, boundary points, so none of the above. So the idea of a boundary point is that it's not an interior point and it's not an exterior point, and so it lies on a boundary. And so our formal definition here says that I guess the empty set is a subset of this intersection between the ball and the set S, which is a subset of the ball itself. Now, the best way of thinking about a boundary point is that you can see that this is informally on our boundary, right? And if we construct an open ball around this point with any radius, it doesn't matter, we can see that it contains points that are inside S, but it also contains points that aren't inside S, okay? So it lies on the boundary of S. Okay, so now we're going to be looking at some types of sets. So given some set, we can classify it in a number of different ways. And so the first one is an open set. So an open set is a set where every single point is an interior point, okay? So that means, to reiterate, an open set, right? I'll just draw a quick example. An open set could be like this, okay? And the key point is that for every single point, so let's say like this point here, we can always zoom in far enough and then draw a little circle around it. That's our open ball, and there exists some epsilon radius, so that this ball is entirely contained within the set. And notice that in this case, we have a dotted boundary. The reason why is because remember, if I have a point on this boundary, then it's impossible for me to draw a ball without it lying with some parts of it outside the set. So that's why we need some dotted boundary. Okay, our second type of set is a closed set. So a closed set contains all of its boundary points, okay? So for example, this set here, but with a closed boundary. So what that means is that the set includes all of its boundary points, and that makes it closed. An alternative definition is that a closed set has an open complement, okay? So if you think about the complement of this set that I've just drawn, it will be everything outside the set, okay? But not including the boundary. All right, so a next classification, or I guess definition here is closure, okay? So the closure of some set is all the points in that original set plus all of the boundary points. So for example, I could have a set like this, okay? Let's say like a set like this, okay, that contains some portion of its boundary. So you can see this solid line is some portion of its boundary, but it doesn't contain all of the boundary. So if this is our set S, then the closure of S, okay, will be the entire set plus all of its boundary points included. Okay, the next definition here we have is bounded. So bounded is fairly intuitive. It says essentially a set is bounded if, so we have this set here, if we can construct some ball centered at the origin that contains entirely that set, okay? So example of an unbounded set would be, for example, this region. So we can't construct a ball that entirely contains that region with a finite radius is the key point. Okay, compact. So if a set is closed and bounded, then it is compact. So that's all we really need to know there. And region is an open set with none, some, or all of its boundary points. Okay, so this is a very general definition here, region. So it's just any open set, and then you can contain none, some, or all of its boundary points. Now, again, sticking to Math2621, we have another definition, which is an arc. So types of arcs. The first type of arc is a polygonal path. So essentially, a polygonal path is just some collection of straight lines, okay? Right? And so the idea is that we can draw these straight lines and then connect them up like this. So whenever I start one line segment, that's the end of another one. And so, you can construct any sort of path in terms of these line segments. Now, a closed polygonal path is a polygonal path that sort of ends where it started. And that's very intuitive. It's just a closed curve. And finally, simple. So if it does not cross over itself at any point in time, then it's simple. So, you could take some curve like this. It crosses over itself, okay, which makes it a non-simple curve, okay? Do we have any issues with the stream at the moment? Let's keep going. All right, so the next thing we're looking at is a domain. So a set is a domain if it is open and polygonally path connected. So polygonally path connected essentially means we can take 2 points within our set, this point, and then connect them using some polygonal path, right? All right, so let's look at a question example here. So describe the following sets in terms of if they are open, closed, bounded, compact, connected, simply connected, or regions. All right, so let's look at the first set. The first set is the set of all complex numbers that have a modulus less than 1. And so this corresponds to the open ball centered at the origin with radius 1. All right, so this one, well, is it open or closed? Well, we know that it's an open ball, so it has to be open. Okay, that means that all of its points are interior points. Is it bounded? Yes, it's clearly bounded because you can just take any larger ball centered at the origin and it'll be contained within it. So yes, it's bounded. Compact. So looking at our compact definition, that was closed and bounded. So if it's not closed, it can't be compact. Connected, if we just look at this circle, clearly it's connected. So you can connect any 2 points. So yes, connected. Is it simply connected? So I think we didn't talk about simply connected yet, but simply connected means that essentially there are no holes within the set. So if there was a hole within the set, then you can't really get this like sort of direct path between the 2 points. All right, so it's not simply, it is simply connected because there aren't any holes. And region, so a region, remember, was a open set with none, some, or all of its boundary points. We do have an open set with none, some, or all of its boundary points. So yes, it's a region. All right, just give me a moment. Okay. We should be back now. Sorry about that, everyone. We're just gonna jump back into it. So to say where we were at, we were looking at sets and then trying to describe them if they're open, closed, bounded, compact, connected, simply connected, or regions. So we're gonna keep going. And the second one we're looking at is this region here, which is the real parts between 0 inclusive and 1. So just looking at this, a good way to kind of figure it out is to kind of just draw it out and then think about it for a moment. So if you can see, not all points are interior points because we have these points here which are clearly on the boundary. But it doesn't contain all of its boundary points because here those points aren't included, which means this is neither open or closed. Okay. In terms of bounded, no, it's not bounded because it's sort of, you can see that it goes up and up and up. So it can't be bounded, so no, it's not bounded. Compact, so it's not closed, so it can't be compact. Connected, yes, it is connected, and it is also simply connected because there aren't any holes. Is it a region? So it's not a region because it's not an open set. Oh wait, let's see. Set. So it is not a region. Alright. And then for the rest of them, we're looking at this point. So we have a single point 1 plus I. So 1 plus I, notice that a single point can't be an interior point because every sort of open circle we make around it will contain some of the points that aren't inside the point itself, right? So it's not open, but it is closed because it counts as a boundary point. And so it contains all of its boundary points itself, so it is closed. It is clearly bounded. Compact, it's closed and bounded, so it's compact. Connected, yes, we can construct a polygonal path between the point and itself. Always. Is it simply connected? Yes, it's simply connected, and it's not a region. And our last point is this sort of annulus. So this annulus will look like this. So we have our modulus between 1 and 2, in which case what we're dealing with is something that sort of looks like this. Okay, and so this region, this set is clearly open because it contains only interior points. It's also clearly bounded. It's not compact because it's not closed. It is connected. It's not simply connected because we have this hole here. And it is a region because it's open. It's an open set with none, some, or all of its boundary points. So we're going to move on from that and to move on to functions now. So a complex function is one whose domain, range, or both is a subset of the complex plane. So essentially we can start putting complex numbers into our functions and getting complex numbers out. Okay, and so a lot of the stuff that from real analysis, so we dealt with like domain, codomain, range, etc., are the same, but there exists some more interesting functions like the modulus or the argument. So the first type of function that we're going to be looking at is something called a fractional linear transformation. And so those are functions of the form az plus b divided by cz plus d, where a, b, c, d are complex numbers. Okay. Now we have our first key information here, and that is, it says here that if f is a fractional linear transformation and z varies on a line or a circle, then f of z varies on a line or a circle. That's to say that the image of a line or a circle will equal a line or circle. So it kind of preserves lines or circles, sorry. Okay, so one thing that we're looking at is what happens as z approaches negative d divided by c. You can see that's a problem because we're approaching 1 divided by 0. Okay, so to do that, we're kind of going to look at a question. Okay, so we have a question here. Consider the fractional linear transformation t of z equals 1 over z plus I. To find the image of the line z equals x plus iy such that 3x plus y equal 1. Alright, so to do this question, we're going to apply this method. So what we'll first do is let z equal x plus iy, which is currently already done for us, and then let w equals u plus iv. In this case, w is the image, okay? So w is the image here, and so we're going to let the image w equal u plus iv. Alright, so now notice that if w equals 1 on z plus I, we can do some simple rearrangement. So we can say wz plus I equals 1. So then we can rearrange to get z equals 1 minus iw on w. Okay? And now what we can do is substitute w equals u plus iv to get real and imaginary parts, kind of. So if we actually make that substitution, what we'll get is this. We'll get 1 on u plus iv minus, we'll get this expression here, which we're then going to simplify to look like this. And then what we're going to do is get rid of this complex imaginary part in the denominator. So to do that, we multiply top and bottom by u minus iv and u minus iv. Okay, and what we get is this expression here. So you can see that from this expression, we have a real part, this, and an imaginary part, this. And remember, this was equal to z, which is equal to x plus iy. So we can equate our real and imaginary parts, okay? So we can clearly say that, okay, x has to be 1 plus u squared on, so 1 on u squared plus v squared, and y needs to equal negative u squared minus v squared minus v on u squared plus v squared. Okay, that comes from equating real and imaginary parts. So from here, okay. Sorry, one moment. Yes, okay, so from here, what we're going to do is now realize that, okay, because our points z lie on a line, we have some constraint on x and y, right? In particular, we need 3x plus y to equal 1, which means that because we have an expression for x in terms of u and v and y in terms of u and v, we can get this to become a constraint on u and v, which in other words gives us the image of the line under the fractional linear transformation, right? So because we have these, we know that 1 over u squared plus v squared plus negative u squared plus v squared minus v on u squared plus v squared must equal 1, okay? And after some rearrangements and completing the square, we get this, which is the equation of a circle. And so this is the image of the line under the fractional linear transformation. So in other words, the line becomes a circle. And in particular, notice that this circle is what? The circle centered at the point 0, negative 1, 4, with radius 5 on 4. So radius 5 on 4. Okay. All right, and our last question to do with fractional linear transformations is a little inequality proof. So if our modulus is greater than or equal to 2, prove that, well, this is not quite fractional linear transformation, it's just a question to do with inequalities. Sorry. So prove that 1 over z to the power 4 plus 1 is less than or equal to 1 over 15. All right, so to do this, we're going to have to remember our two key inequalities. So that was triangle inequality and circle inequality. So the first thing we want to notice is that we want to use the circle inequality. The reason why is because what we have is a modulus on the denominator. So we have a z to the 4 plus 1 on the denominator. So if you applied your triangle inequality, you get something like this, right? But the issue is that we have a less than or equal sign here, which gets flipped when we have to take the, I guess, reciprocal, right? And so what we're going to notice is that we want to use the circle inequality instead, because we have this greater than or equal to sign that gets swapped to this less than or equal sign when we reciprocate it. So applying the circle inequality, we get this result, okay? And you can simplify that a little to get this. All right, so now notice a few things, right? If z is greater than or equal to 2, the modulus of z, that is, then clearly, then clearly we have z to the power 4 modulus is greater than or equal to 1, okay, which means we can drop these absolute value signs here because we know that this thing's always positive. Okay, and now we can apply the inequality again because we know that z to the power 4 must be greater than or equal to 2 to the power 4, just based on this inequality. And so what we get is 15, and so if we flip it all, then we get just get our required result of this inequality here. So I'm going to hand over to Marcus now, who's going to do limits and differentiability.
Hello. Hello. Okay, we'll just make sure the audio is working. Okay, it is. Alright, so limits and differentiability. Let's get into it. So first off, what is the existence of a limit? So a limit is said to not exist if the limit attains different values along different paths. So before in like real, we had like you either approach from like the negative or the positive, but in complex you can come from like all sorts of paths, right? To a certain point, you can come from here or wherever. So the limit does not exist if you get different values if you take a different path. Alright, so if it does exist, then it must satisfy these conditions here, this definition. So for every epsilon greater than 0, there is a delta greater than 0 such that the size of this, which is less than delta, then means that the function value minus the limit is less than epsilon. And yeah, we've just simplified it here. F of z gets close to the limit L whenever z gets close to z0. Alright, so our first example is proving that the following limit does not exist. So first we'll rewrite z as r e to the I theta. And we can observe here that as we're observing the behavior of the limit z is approaching 0, we also have to set this r to approach 0 as well. So now we can just substitute this in, and we'll get this line. And next, remembering that e to the I theta is r e to the I theta is this. Okay, so the imaginary part of this is going to be equal to r and the coefficient of I, so r sine theta is on the top. And we can see here that the r's will then cancel out, and we're left with this term here, sine theta over e to the I theta. And you can see r is not even involved in this equation, so we can simply get rid of the limit. And we're now left with this value here. So we can see that this will actually have different values. This term here will have different values depending on what value of theta we choose. So that means that the limit does not exist because it is like multi-valued. It has different values. So yep. Next, continuity. So it's continuous if the limit of the function as it approaches a value is equal to the value, is equal to the function when you sub in that value. And as a result, any combination of continuous functions will also be continuous. Okay, so first we prove that this first example is proving that f of z equals the imaginary part of z is continuous. So we have to prove from the definition that as we approach the function, the function value will approach the value of the function. So we use the definition of the limit. So for all epsilon greater than 0, there exists a delta greater than 0 such that this condition is going to be satisfied. So we let epsilon greater than 0 and we choose a delta. For now it's just delta, and yeah, we'll just observe what happens when we put it into our definition. So we have the imaginary part of z minus the imaginary part of z0, the modulus of the difference. And remember that we can actually combine the two values, the two complex numbers, under one, just the imaginary part of that. It's the same thing. And next we can observe that the imaginary part of a complex number is less than or equal to the size of the complex number. So if this is an imaginary number w, then you can see the imaginary part is just going to be this height here, and this is a right angle triangle. So we know that the hypotenuse, which is w, is going to be greater than or equal to this side here. So that's why we can have this line here, this inequality. And this is from over here less than delta. And we can actually choose a delta as epsilon, because if we choose this as epsilon, then that means that our inequality will become this if we take it back all the way to the top, and that will satisfy our condition that we were looking for. So hence we've proved that the limit, the function value, the limit of the function as it approaches this value is equal to the value of the function at that value. So we can say that it is continuous. Next we have differentiability. So a function is differentiable if the following limit exists. So you probably recognize this as quite similar to real. Differentiability implies continuity, and yeah, it's pretty similar to real numbers. So we say that this function, when you split it up into the u and v, the coefficients of the real and the imaginary, is differentiable at an interior point in the domain if and only if the partial derivatives of u, v all exist and are continuous and satisfy these Cauchy-Riemann equations. So these are very important equations to know. So just note the negative sign over here. Alright, so, and if it does exist, then it is given by this equation here, where these are the partial derivatives of u and v with respect to x. Alright, so we've got a few functions here and we have to determine whether or not they are differentiable. So first of all, we'll just separate it out into the u and v, because that's what the form we're looking for, is the u and the v form. So doing so will give us this. So this is now our u of x and y, and this is our v of x and y. And now we just need to satisfy the Cauchy-Riemann equations. So to do that, we just calculate the partial derivatives of u and the partial derivative the partial derivative of u with respect to x. Okay, sorry about that. Yeah, so we just calculate the partial derivatives with respect to x and with respect to y. So I'm sure you could do this. And yeah, we just need to find out when these equations satisfy the Cauchy-Riemann equations. So we first have the uy equals vx, negative vx. So we have 2xy is equal to negative 2xy. And this is only satisfied when xy is equal to 0. Right, so then the next equation is going to be this first term is equal to the fourth term. So rearranging this actually gives us 2x squared equals 2y squared. And this is satisfied when x is equal to plus or minus y. So now we just have to combine these two equations and see when these equations, the Cauchy-Riemann equations, are satisfied. So we can see that x is 0 and y is 0 is the only solution, and therefore this function is only differentiable at the origin. So just recap what we did. We split it up into u and v. We then calculated the partial derivatives. Then we subbed it into the Cauchy-Riemann equations to see where it satisfies the conditions. And we just found the overlap of the two conditions that we found. And therefore, we found out where it is differentiable. Alright, so we'll apply that again. It's already in the form u and v. So we'll just calculate the partial derivatives. And you can see here, so our first one is going to be these middle two are equal to the negative of each other. So this is always true, no matter what x and y we choose. And then next we have 3x squared equals 3y squared from this equating to this. And this is satisfied when x is equal to plus or minus y. So both of these conditions are satisfied when we have, because the first one is always true, we just need to know the second, when the second one is true. So we can just say it's differentiable whenever this is the case. Alright, moving on to the last one. So this one can look a little hard at first because you're wondering, how do I differentiate the modulus? But what we do is we rewrite the modulus as a trick. Rewrite the modulus as the square root. So say the modulus of x, we write it as the square root of x squared. And now just using chain rule, differentiating this. So we'll end up with 2x differentiating the inside, and then minus, 1/2, and then to the power of negative 1/2. So this is gonna be equal to x over, and remember not to simplify this again because it is not x, it is the modulus of x. So yeah, that's how you calculate the differential of the modulus. So anyway, putting that into the equation, so again we have when these are equal to the negative, and then when the first is equal to the fourth here. So that one's always true. And then we have this condition, and we'll just simplify it or rearrange it. So multiply both sides by modulus of x and divide both sides by y, and we're left with this. And you can see that because also it's important to know that x and y are not equal to 0 because of they're on the denominator. Now we can see that x over y is greater than 0 because no matter what is in this modulus here, this is going to be positive, meaning that x over y has to be positive, right? So that means that the function is differentiable when this is satisfied, which means x over y is greater than 0. So when that is satisfied. Sweet. Okay, so now holomorphic. So we just got this definition here. Suppose that omega is an open subset. An open subset is quite important. If a function f is differentiable in omega, then f is holomorphic, and we can use this notation here. And a function that is holomorphic in the whole complex plane is called entire. So a function can only ever be holomorphic on an open set. If a function is differentiable in a closed set, it will not be holomorphic. So yeah, there is a distinction between differentiable and holomorphic. Mainly, yeah, just this open, it has to be open set for holomorphic. Alright, next we have harmonic functions. So harmonic functions, it just has to satisfy the Laplace equation, which is the second partial with respect to x plus the second partial with respect to y of u is equal to 0. And also that the first and second partials exist and are continuous in the domain that we are observing. Next, we also define a harmonic conjugate is the v. So remember this harmonic, we're looking at just the u. And then the harmonic conjugate is finding this v such that it is holomorphic. So remember, holomorphic is differentiable on this open set. Right, so we're just finding the v such that it's differentiable. So applying these definitions, so we need to show that u equals sine of x sine of y is harmonic, and also find a harmonic conjugate. So first off, we'll show that it's harmonic. So to do so, we'll look at the partial derivatives. So first we'll calculate with respect to x, it's pretty simple, and with respect to y, it's also pretty simple. And you can see that when you add them together, it is going to satisfy our equation to equal 0, and therefore we can say that u is harmonic. So next we have to find a v such that it is holomorphic. So remember, to be holomorphic it has to be differentiable. So in order to be differentiable, it has to satisfy the Cauchy-Riemann equations from before. So we already know the partial of u with respect to x, right? We calculate it up here, and we know that the partial of v, the function we're looking for, is with respect to y is also equal to this, and similarly this. So yeah, we just need to find a v such that we satisfy these Cauchy-Riemann equations. So next we can integrate with respect to y to, well, I guess find the antiderivative. So when we observe, we're observing this one here. So remember, we found this over here. And to satisfy the Cauchy-Riemann equations, we need this v with partial respect to y to equal this. So now we just reverse that to try and find v. So we integrate with respect to y. So this shine term turns into cosh, and we're also left with a constant with respect, a constant that can contain x, since we did partial with respect to y here. And then we can just, so we went from partial y, and then we went to v, and then now we'll go to partial x, and that should allow us to find the constant c. Okay, so yep, so using our result from here, v, this result, differentiate with respect to x, and that will give us this. And comparing our results over here, which is the negative of this, we can see that the value of this constant with respect, that's being derived with respect to x, is just going to be 0 in order to satisfy our equation over here. Alright, so we calculate that the constant that has been derived is equal to 0, therefore the constant is just c, a real constant. And we can just let this be any answer is valid. You c is equal to 1, -1, whatever number you want. The question just asks us to find a harmonic conjugate. Of course, there's going to be multiple in this case, so we'll just pick c equals 0 because that's the simplest one. So a harmonic conjugate is equal to this. So just to recap, to find that it's harmonic, we just found the partial derivative twice and then set it to 0, and it satisfied this equation, so it's harmonic. Then we found a harmonic conjugate by finding this v is the harmonic conjugate. So we just used our equations from before, satisfy the Cauchy-Riemann equations, and we just combined them and integrated to find the constant, and then eventually find a specific harmonic conjugate. Sweet. So next we have the exponential series, which is defined by this Taylor series. Should be familiar to you. So the properties, probably also familiar with this, these properties here, and this will probably come in use later, the periodicity, just observing that it is repeated. And we define this because this will be used to define all of our other functions as well. So as you can see, the hyperbolic, cosine and sine, or cosh and shine, so we can define them in terms of exponential, and then using our result here, we can then have this Taylor series for them. Okay, so we've got some properties here which translated from our real analysis. So yeah, you can just see the addition and the derivative of cosh and shine. You should be familiar with these. Alright, so we got some properties here. So we have got cosh is even, shine is odd, and because we're defining these in terms of the exponential, and the exponential is periodic, then these functions as well are also going to be periodic, right? And yeah, you should know this one as well. This is also translated to the complex. And next we have cosine and sine. So similarly, we've got the exponential, and then we got this we got this Taylor series here, and we've got some properties here which are very useful. So you should definitely know these. Just converting from sine and shine, or cosine to cosh. Right, so now we've got the logarithm and the complex. So the principal branch, which is going to be denoted by this, we've got this capital L for log and capital A in arg. So this is our definition of the principal branch. So of course the argument is going to take values in this range, negative pi to pi, and log is differentiable everywhere apart from the negative real axis. So differentiable everywhere apart from this, just this line here. Okay. And next we also have the multi-valued log. So what this means is basically the arg here is periodic, so we have many values. So basically the main difference here is in the principal value, the principal branch of the logarithm, we just have the arg value which sits in this range, whereas the multi-valued we have, of course, multi-valued arg here. Yep. Okay, so we've got an example here. Solving cosh of z is equal to -2. So this is going to be, of course, complex, because in the real, cosh does not approach -2. Okay, so first of all, what we'll do is we'll rewrite this in terms of the exponential form. And what we'll do is we'll rearrange the equation to become a quadratic. So now we've got this quadratic here, and we can use the quadratic formula to solve for e to the z. Okay, so we've subbed into the quadratic formula, and now we've been given these two values for e to the z. So you can note that both of these values are actually lie on the, so say -2 is here, and -2 -2 plus 3 is going to be around here, and -2 minus 3 is over here. So they're all lying on the negative real axis. Alright, yeah, so we take the multi-valued log of both sides to get rid of the e there. Okay, and by definition, we have the natural log of the modulus here, and the arg of this, the multi-valued arg. Alright, so basically, because, as I was saying before, both of the values lie on the negative real axis. So both of these values lie here, which means that the we will take the modulus in both cases, which means we can flip this here and make it positive. And also for this arg, which is the multi-valued arg, that's where the I, this term here, I pi, has come from. So you can see that this is a value of pi. So that's where we got the number from. So there might be a case where you might actually have to split, say this was plus or minus square root 5 here instead. So you would have to then split it into like two separate cases, but in this case we just have 3 and they're both negative, so they both have the same arg value. And of course, as it's the multi-valued arg, then we can just use plus 2k pi I over here from this I. Sweet. So now we're going to be looking at branches of logarithms. So we have this definition here for any real number theta. So what this actually means is that the value of arg here is in the range of theta to theta plus to pi. Right, so we're just like redefining what the arg here is going to give us. And it's also important to note that the branch cut is when this loops around. So say we have say this is theta here. So the branch cut is going to be here. And the branch cut is important because everywhere else is differentiable apart from the branch cut. So we'll use this to move around where it is differentiable, because remember from the principal branch of log is not differentiable on the negative real axis, and we might want to move that in case we want to observe some behavior there. Okay, and also the derivative is just like the real 1 over z. Okay, so here's the example I was talking about. So we need to find a branch such that it is continuous at z equals -1 and has a value 7 pi I. So yeah, as I was discussing before, we can't use the principal branch of log, because by definition, in the definition, it is not continuous in this negative real axis. So we can just take the branch cut along the positive real axis, right? So that's probably the simplest one. We can pick another one, but that's probably the simplest one. So this implies that we'll have some 2k pi here, ensuring that the branch cut is on the this real axis here. If it's every 2k pi, it will be on the real axis. And yeah, so this is just the definition of the branch of log. Okay, so then we just substitute in. So when we substitute in this, of course the definition is actually the natural log of the modulus, but this will become 1, and then this term will become 0, so we just ignore it for now, or we ignore it completely. And then we're just left with I arg of -1, and we need to satisfy 7 pi I. So we can just choose a multiple of 2k pi such that 7 pi will fit within this range. So we just pick 6 pi to 8 pi. Pretty simple. And yep, there we go. We'll just write it formally. Theta is equal to 6 pi, and the branch is defined by this. Okay, so we want to, this new example, we want to determine where the function z, where the function is the principal log of 3iz minus 4 is differentiable. So remember, it is not differentiable on the negative real axis, but it's differentiable everywhere else. So it is not differentiable when whatever is in the log is part of the set. So what we can do is we'll just rearrange for z. So rearrange for z, and here we need to find, we'll just rewrite this as a new constant k. So if we put in negative, okay, rewrite this, so negative 4 plus lambda over 3. Okay, so because it's negative, it's going to be flipped. So we'll sub in 0, and then you get negative 4 over 3, which is this value here, and then we'll sub in negative infinity, and that will give us positive infinity on top. So that's how we get the other part of the top part of the range. Alright, so that's where f is not differentiable, which means it's differentiable everywhere else. And this, we can actually draw it out. So this is real, this is imaginary. I've got this value here of negative 4 over 3. So it's not differentiable along this line here, but everywhere else it is. Alright, next example, find all complex numbers z such that the sine of z is equal to 2. So similar to our example before, we'll just write it in terms of the exponential. Okay, let me just test it's working. Okay, yeah, it is. So yeah, as I was saying, write it in terms of the exponential and rearrange to get to a quadratic. So we've got this quadratic here. Just simplify. Alright, and then we take the log to get rid of the e. And yeah, so we're gonna have two different cases here for the plus and minus. Right, we're just subbing in the definition of the multi-valued log. So okay, we'll just take the first case here, which is the plus and the plus or minus. Okay, so we've got I multiplied by z is equal to the log of that. And we'll just evaluate. So this will be 2 plus square root of 3. Remember, because the modulus of I is just going to be equal to 1, so it disappears. And then we've got the multi-valued arg of 2 plus square root 3i, which means it's going to be on this positive imaginary, so it's going to have a arg of pi over 2 plus 2k pi, and don't forget this I term here. Okay, and then we'll divide everything by I to find z. Alright, so now we've got the second case where we have minus. So in this case, again, we have the I disappears, and we have the same theta here. And we're just left with this, which is very similar to the one before. So you can see here, there'll be a lot of questions like this. I'm sure you can practice, but essentially we wrote it in terms of the exponential and then rearranged for a quadratic, and then used the multi-valued arg and found the different solutions. Alright, so now we've got complex powers, the principal branch. So the principal branch of z to alpha is equal to the exponent of alpha multiplied by the principal valued log of z, and the multi-valued function is defined by this. So basically, again, the main difference between these two is this is going to be multi-valued for the argument here. Right, and complex roots, this is also useful. So we just have this definition here of modulus of z to the 1 over n multiplied by e to the I arg z over n. And this is principal branch, so we don't have these like multi-valued here. Yep. Okay, so we'll find this and the principal value of it in the form x plus iy. So we need to use our principal value here and substitute in. So we have e to the alpha is the exponent, and we have z here and the principal log here. So we have the exponent here, alpha, and the value z here, so this is log I, which gives us natural log of the modulus of I, and also I times arg here. And simplifying again, this value will become 0 as the modulus of I is equal to 1. And yep, we've just rearranged, like factorized a bit. Alright, and now we've multiplied in this 2i over here, and this remember, like adding exponents here is the same as multiplying them on the outside here. And e to the I pi plus 4k pi, so we can essentially ignore this. So e to the I pi is -1, so that's where it's gone. It's just become -1 here. Alright, so the principal value of this is equal to the negative e to the pi over 2. Alright. Next question, where is this function of the principal value of the square root of z squared plus z to the -2 analytic or homomorphic? Where is f of z continuous? Alright, so first we'll look at we'll just split up the function, of course. So we'll consider the principal branch of just the square root. So going back to our definition over here, this time n is going to be 2. So we can just substitute that into our equation. And we know that the principal value of the square root is differentiable on C, excluding this, right? Because the arg of z, the arg of z is not differentiable along this negative real axis, because that's like where the range hits each other. So oh yeah, and the square root is similarly, the square root is continuous on this, but the only difference here is that it is continuous at 0. Alright, and this is actually, these are true for all of the roots, values of n, positive integers of n. Alright, so consider writing it in re to the I theta form. So we've just written it there, and then we've written e to the I theta as cosine theta plus I sine theta. Just looking at what's inside the square root now. Alright, so now we're going to be looking at where, remember we're trying to find out where it is analytic and where, which is differentiable, allomorphic, and where it is continuous. So commonly we just find out where it's not, and then and then it's just everywhere else. So where it's not is going to be the negative real axis. So that's what we're going to be looking for. We're going to be looking for the negative real axis. So we look for this in the inside to be real, and this is real when this coefficient here is equal to 0, and this is going to be equal to 0 when either this bracket here is 0 or sine to the 2 theta is 0. So that is satisfied when r is equal to 1. This will become 0, or in the case that 2 theta here is a multiple of pi, right? Okay, so for it to be real, then it has to be on the unit circle, because r is equal to 1 will give us the unit circle, or the imaginary axis. So the imaginary axis, because 2 theta has to be a multiple of pi, so pi is here, so 2 theta is going to be on this part of the imaginary axis, or on this. That will satisfy our conditions here to be real. Okay, and if we just let z is equal to it, so this is the case where it's on the imaginary axis, right? It's just this case here. Then when we substitute in, we find that because t is a non-zero real, this value here is going to be less than 0. So what we've shown here is that when it is real, in this case where 2 theta is a multiple of pi, then it's on the imaginary axis, and then we've let it be on the imaginary axis where t is a non-zero real, and we've shown that if it is on the imaginary axis, then it's going to have a value less than 0. So it will be negative. All right. And if we let z equals e to the I theta, then when we substitute it into here, this actually simplifies to 2 cosine 2 theta, 2 cosine 2 theta, yeah, which is negative or 0 when theta is in this range here, right? Which is like this. Okay, so we know that the principal value of the square root is differentiable on this area, and we also know that this inside the square root is in this range, same range here, if it is on the imaginary axis, right, because of that 2 theta thing, not including 0, and on the unit circle when the argument is in this range here. So we consider the set, we just define this set as not including 0, and this is the unit circle, and this is the argument here. Alright, and yeah, we don't include 0 because of the z to the minus 2. So it is going to be analytic or holomorphic on the set here, so not including. So once again, what we did was we found where it's not differentiable, considered when that would be the case, and we found that would be the case when it's on the unit circle or the argument holds these values. Therefore, it is analytic on C apart from this set here. Alright, and similarly for continuous, the only difference here is that we now can include 0, so we'll just find out where it is equal to 0. So we'll just do some simple rearranging here. Z to 4 equals -1. Find the solutions for that. And okay, so basically the answer for this is the same as the set A that we defined here, except we subtract the values of 0 because we don't want to remove them from our set because it will be continuous at 0. So that just leaves us with that. Hopefully that will make sense. Okay, and now we will, actually I'll just drink some water. Okay, so curves on a complex plane. So curve NC is a continuous function where we've parameterized it. So the initial point is going to be gamma of A and the final point is gamma of B. The range is the set and a curve is closed. This is similar to what Lachlan was talking about before. It's simple if it does not cross over each other except for the endpoint, and it's closed if the initial point and the final point are the same. You can have a simple closed or Jordan curve if it satisfies both of these. Right, so this is once again similar to what Lachlan was saying before. So this one is simple because it does not cross over itself at any point, and it is not closed because the initial and final point are different. And this one is not simple because it crosses over itself, and is closed because the initial and final point are the same. And this is satisfying, the last one here, the semicircle, is satisfying both. So it's a simple closed / Jordan curve. Alright. Okay, so we now have the definition of a join. So we can have two curves and we can join them together. But the requirement, of course, is that the final point of the first curve is the initial point of the second. Alright, and we also have the reverse curve because when you parameterize it, you'll be traveling in one direction as you increase in t. So then we have the reverse curve, which is, as the name suggests, it's just the other direction. So it's just defined by this. Alright. And yeah, we got the parameterization of lines and circles. So this is similar to vectors, so you just have your initial point and your second point, and then you just have t, which is like the parameter here, and the the direction of the second point from the first point. So you have z0 here, z1 here, so this will just be a parameterization of, if I make it a straight line, yeah, should be quite familiar to you. And a circle is going to be in this form, re to the I theta, where re to the it, where t is in this range here. And z0 is going to be the center of the circle. So if this is our origin, then we have, say, z0 here, and r is the radius, and that's a circle. Yep. Alright, so we have the derivative, so basically we've just split it into the imaginary and the real components, and we've taken the derivative here. And we say that it's continuously differentiable if the derivative exists and is continuous on this interval here. And we say it is smooth if it is continuously differentiable and the derivative is not equal to 0 for all values in the interval. And we say it's piecewise smooth. Gamma is piecewise smooth if it is a finite. If it is a finite join of all of these which are smooth. So I'll just give an example here. So each curve individually is smooth. However, as a whole, it is not smooth because you have these points here which are not differentiable. So that's why it's considered piecewise smooth, because on its own each value is smooth. Alright, so we know that this curve here is smooth. It's just yeah. So it's just this line here. Is this curve smooth? Where we've got t cubed plus I t cubed smooth. And we'll just consider the derivative when t is equal to 0. So we'll derive this. And at t is equal to 0, when we sub in into the derivative, we actually get that this derivative is equal to 0, which does not satisfy the requirement to be smooth, which is that it is not equal to 0 for all values in the interval. So we can see the initial one is smooth because when we derive it we get 1 plus I, and when we sub in t is equal to 0, this is not equal to 0, so it is smooth here at 0. But for this t cubed plus I t cubed, we get 0, so by definition it is not smooth. And if it is not smooth, it cannot be piecewise smooth. Yeah, so another interesting thing is that although both of these functions have the same line, but it's actually what matters is the rate at which it travels along the line. So yeah, we have to check the derivative to see whether or not it is actually smooth. It's not just the line itself, the curve itself. So yeah, there has to be no sharp corners or cusps, and it also has to not stop, it has to keep going. Alright, so now we've got the next definition. The length of a piecewise smooth curve is denoted like this, where this is like the real, oh no, t plus t squared. Okay. So yeah, I'll explain it more in an example. So finding the length of this curve, what we'll do is we find the derivative and we find the modulus of the derivative, and done this so many times, but the modulus of I is 1, so it's irrelevant. The modulus of e to the I t is also 1, so we can just get rid of it, and then we just have left with this integral here with r, and we're integrating with respect to t, which means we just substitute in the bounds and we get to n pi r. And oh yeah, it's also important to note that r is greater than 0, so that's why we can get rid of the modulus signs here. Right. So the definition of a contour. So a contour is the oriented range of a piecewise smooth curved gamma. In other words, it is the range with some orientation describing how this set should be traversed. So that's a mouthful, but basically it's saying like the direction, or yeah, basically the direction, which is typically anti-clockwise. So then we traverse it, yeah. Oh yeah, it has to be simple, otherwise it doesn't make sense. Like you'll have intersections and then you don't know which direction to go. So yeah, once again assuming that anti-clockwise, unless it says, and yes, so a contour is a range while a curve is a function. There's a distinction between the two. Alright, moving, that is useful for complex integration. So we define the integral of a complex valued function where we have the u and the v as this. So essentially it's the same as real integration, except we just treat I as a constant here. And some useful properties which we will apply is that the real part of the integral is equal to the integral of the real part. And similarly, the imaginary part of the entire integral is equal to the integral of the imaginary part of the function. Right, so once again, it's really similar to real integration. We can split up the integral into different parts, and we can take out constants. We have like reverse chain rule, we have integration by parts, and we also have this here. So the modulus of the integral is less than or equal to the integral of the modulus of the function. So this might be new, might be not new at all, but yeah, that is useful as well. So getting into an example, we've got this integral here, e to the t cosine t dt. So we can see that cosine of t is equal to the real part of e to the it, and e to the t is real, so we can just combine it all into one. And we can integrate like this. So remember applying that from before, the real part of the integral is equal to the integral of the real part of the function, so we can just take the real part out and integrate it. So we evaluate the integral of this, which is easier if we just combine it into one term, e to the 1 plus I brackets multiplied by t. So we just evaluate this like I is another real constant, so we just divide by this term here, and we have our bounds here. Substitute in our bounds, just multiplied top and bottom by 1 minus I to rationalize the denominator. That's why we've got this here. Substituted in our bounds, we got this, and then we got this when we substituted in 0. And going back to what we had before, the integral of this is equal to the real part of this, which is the real part of the integral, and this is the integral that we just calculated. So we take the real part, so we have e to the e to the 2 pi, e to the 2 pi I, this one. So this e to the 2 pi I term here, when we've expanded this bracket, is actually equal to 1 here, so that's how we've left with this. And yeah, we're just taking the real part, so we can ignore that. All right. So, given a piecewise smooth curve, we define the complex line integral as this. So this is pretty useful. But yeah, basically what we've done is we've just used the substitution z equals gamma of t, and we're left with this formula. So an example of using this formula, so you need a piecewise smooth curve to use this. Oh, sorry, got some theorems here. So this is similar to before. We just have like the it's like linear, so you can split it up. And here, when we're integrating with the reverse, we just have like the negative here, negative sign here. And it's piecewise, so we can actually split up the integral into different parts, if that makes it easier, and it's still going to be the same value for the integral. Alright, so moving into the first example, evaluating this, where gamma is given as the unit circle. So using our formula here, we will have first define gamma as it is the unit circle, so it's just e to the it, you should know this, with this range of t, and then we differentiate because that's what we need for our formula, which of course just differentiate with respect to t, so we just have this I carried down. Then we substitute in, so we have our bounds is the endpoints of our interval of t, then we substitute it in gamma into our z, so we're left with it squared, and then we multiplied by the differential here. So yeah, once again we just used this, so we have the function of z, so this in this case was z squared, so then we're left with gamma squared, and then we multiplied by the derivative. And then after some simplification, we have this, and when we integrate so when we integrate, the i's will cancel out, and we're just left with e to the 3it over 3. Substitute in the bounds there, and it will equal 0. So next example, we have the integral of the conjugate of z, and we're given the gamma here. Right, so once again we just apply the formula, so our bounds are the endpoints of the interval of t here, then we substitute in gamma for z, and multiply by the differential of gamma, which can be 1 plus 2it, and differentiate with respect to t. Substitute in, so we left with the conjugate of this conjugate, so we just flip the I there. Then we expand out, we get a cubic, easy to integrate a cubic, substitute in, and we're left with this value here. Sweet, so yeah, okay, basically we just use this formula here, substitute in the bounds, and that's all that we have to do. Okay, so you may have noticed that we can actually write a curve, the same curve, in different ways. But what happens is that, okay, well, yeah, first we'll define it. So basically it's just a reparameterization. So it's the same curve, but it's like it got a different parameterization. But what we notice is that we actually get the same value no matter what parameterization we choose. We will have the same value in the integral. All right. So next we have the ML lemma. So the size of the integral is going to be less than or equal to the maximum value multiplied by the length. So if you think about this in like real terms, if you have an integral, here, it's much simpler because you just have like the length here is gonna be like between A and B, and then the maximum value is the like tangent of the top here. So then we just have like a rectangle where this is gonna be M, and then this across is gonna be L. So you can see like how they've gotten it. So basically this, which is the red under the curve, is less than M times L, which is this whole thing. But that's for real. We are dealing with complex. So how they do this is M is going to be the maximum distance from the origin instead, because our curves are going to be looking something like this. So what you do is you find the length. So the length of the curve is like that whole thing, and the M is going to be the value with the largest distance from the origin. So here would be like this, and then you like multiply by the length, and therefore the value of the size of the integral here is less than the whole thing over here. So that's how I think of the ML lemma. Alright, so yeah, so M is like the largest value of the modulus on the curve. Alright, so we're applying this, showing that when traversing anti-clockwise, this will approach 0 as r approaches infinity, where r is like the radius of this semicircle. It's a semicircle. This is r, the radius, and as it approaches infinity. Alright, so from the circle inequality, we get this, and the modulus of z is equal to r, that is we've defined in our curve. So we can take the reciprocal of both sides, flip the sign, and we're left with this here. Now we have, because we're using the ML lemma, we need to multiply by the length. So the arc length of the semicircle will be equal to pi times the radius r. So yeah, so the maximum value is going to be this, and then the length is going to be this. So by the ML lemma, we have this equation, and as r approaches infinity, obviously this denominator is going to become much larger than the numerator, so the result is true, and this will become 0, which means this is less than or equal to 0. So this is less than or equal to 0, so the result is true. Alright, so given a contour, we define the contour integral like this, where gamma is any parameterization of the contour. And it doesn't matter which parameterization we pick. Alright, so Cauchy-Gaussat theorem. So suppose we have a simply connected domain, and if is holomorphic, and this is a closed contour in omega, then we can say that the value of the integral is going to be equal to 0. So basically, we need that it's holomorphic in the whole domain, and it's simply connected domain. Then, yeah, it will equal to 0 if we choose this closed contour. So we've also got this here, which is basically just saying the sum of each contour is also going to be 0, like each individually is going to be 0, and the sum of all of them are also going to be 0 when we're taking them in anti-clockwise. Right. Plus, that's plus. So we've got a basic thing here where gamma is the unit circle. So this value here of the function is holomorphic everywhere apart from this point here, but this point here is outside of the unit circle, which means that we are holomorphic, which means we can apply the Cauchy-Gaussat. Right. So by the Cauchy-Gaussat, because it's holomorphic on and inside, then the integral just evaluates to 0. So it's pretty simple. Alright, and yeah, this is similar to before. It's just stating that if you have two contours with the same initial and final points, it doesn't matter which one, it's going to be the same integral anyway, same value of the integral. Alright, so we have primitives exist, similar to real. It's just stating that you have the primitive or antiderivative. You can just substitute in if you have that. Alright, so an example of this. Let gamma be any contour from I to negative I which lies entirely in the set where the real is negative. So it's any contour from I to negative I, but the entire set has to be negative. It cannot go into the positive real axis, or positive real side. Right, so because at first glance it looks like you want to use log, but log is not differentiable, so it's not holomorphic along this negative real axis. So we need to choose a different branch. So yeah, we cut through there, so we can't use the principal branch. So we'll just use the branch cut that's on the positive real axis. We can pick any, it doesn't have to be on the positive real axis, it can just be, it could be this one, it could be that one, but positive real axis is the easiest. Right, so we have the log of 0, so remember this means that it's between 0 and 2 pi, which means our branch cut is going to be at 0, which is over here on the positive real axis. So we've got the definition here of the branch that we selected, and we substitute in, and it's differentiable anywhere apart from the line 1 to infinity. The 1 comes from this z minus 1 here, making this 0. Alright, which means we can apply this branch to our question, because it is holomorphic everywhere that we need it to be. Alright. So yeah, we've got a valid choice for the primitive. So yeah, we just had like the integral of this, attempted to use log, and now we've chosen the branch of log, which is holomorphic along our gamma. So that's why we can just state that the primitive, or like the integral of this, is the log with the branch at 0. Alright. So if we just calculate this, substitute n. So we substitute n to our two values. So we're calculating from I to negative I to I. That's where we've gotten these from. Substitute n, simplify. This is a value of root 2. The arg of this is down there. I think you can follow. These will cancel out. And we have to choose, remember, because we're dealing with log 0 here, we need the log to the argument to be between 0 and 2 pi. That's why we add 2 pi here, and that gives us our final answer here. Alright, so this is our next question here. This is a long question. Alright, so we've got to evaluate this, and we've been given a hint here by integrating this, but they don't give us a contour, so we need to evaluate this. Alright, so we want to integrate along the real axis here, because based on our limits, so we'll just start with the line negative r to r, and what we'll do is, because we can't have, like, a contour is not defined if it has infinity, so what we'll do is we'll just define it as r and then observe the behavior as r approaches infinity. Yeah, that's what it says. And this function is not defined as x equals 0 because of the denominator here, so we can avoid it by going around this point with an arc. Alright, so we're just like creating our contour here, so we don't want to include 0, so now we've got this semicircle here, and we use epsilon as the radius of this circle. Alright, and yeah, we'll just take a limit as this approaches 0 later on. Okay, and contours are usually closed by an arc. This is going to be useful later. So we can just close it by the semicircle here with radius r. So it's all contained. Alright, so yeah, as stated before, we want to take the limits r approaches infinity and epsilon approaches 0 at the end. Okay, and since the contour is closed, we can use the Cauchy-Gaussat theorem, which means that basically we've split up the contour into the different parts, and as a whole it will be equal to 0 from the Cauchy-Gaussat. Yep, and then we just split it into, so this is like each part here is split into a different integral. Alright, so we'll just evaluate them individually. Yeah, we're dealing with x here, so we'll change this e to the iz to just become x, z equals x. It's fine to do that because we're not changing anything. Okay, and then that's this first integral. Changing an x because we need to deal with x. Next, we deal with the next one, but we also want the, looking at our bounds here, we want the bounds to be the same as the first one, so we'll have to change that. In order to change that, we'll just use, instead of subbing in z equals x, we can sub in equals negative x. Okay, yeah, so as stating before, we need the bounds to be changed. So substitute in, let z, this is, once again, it's like a substitution, pretty simple, differentiate both sides. and find the new bounds. Alright, so we substitute it in, and then we just flip the bounds by taking the negative, and that'll give us what we want, right? So move on to the third integral. So this is the like small semicircle. So we take the reverse here, and we define the reverse as this, because remember, like, we're traveling. The reason why we take the reverse is because we need to travel around this whole contour, like the 4 bits together, as like one whole. So say we follow this route here, anti-clockwise, and then along here, and when we evaluate this contour, we need to travel clockwise along this one. So that's why we're taking the reverse of this one, because we need to create like a loop. Alright, so going back to that's why we picked the reverse, and we let it equal to this, where this is the semicircle, this is the radius. Alright, so then we differentiate, and yeah, we can just substitute into the formula from before. So we substitute in the reverse contour as our z, multiplied by the derivative, and then after some simplification, we are left with this. So this will cancel, and this will cancel. Yep, and then we just take the I out. Alright, and once again we're observing as epsilon tends to 0, which means as epsilon tends to 0, the exponent here will also approach 0, which means this is e to the 0, integrating with respect to, that should be t, but anyway, either way will get you negative I pi. Alright, and then the last one here, which is the big semicircle. So we'll parameterize it like this, differentiate, and once again we substitute in z as the contour here, and multiply by the derivative. Alright. Oh yes, and we will be taking the limit as r approaches infinity, and we'll be using modulus to let us, because we can remember this rule from before, this is less than or equal to, the modulus of the integral is less than or equal to the integral of the modulus of the function. So imagine it was like a real function and it went like this. The modulus of this integral is going to be less than if you took the integral of the modulus, which would have this bit here. So that's why that's true. Nope. Alright, and we're evaluating this one. So evaluating this one so that we can try and set it to 0. Splitting up the terms, we get I, modulus of I is 1, modulus of e to the I r cosine of t, that will also approach 1, because like this is e to the I theta essentially, so it's just e to the I, well yeah, so it's going to be on like it's going to have a value of 1, it's going to be like here. Anyway, next we have this term which does not go away, and we just left with this, and observing here with the r approaching infinity, because t is between 0 and pi, that means it's going to be non-negative, which means when we put in this negative infinity here, it's going to stay negative, which means that this is going to approach 0, which means the integral is going to approach 0 as well, which is greater than or equal to this integral, which means this is 0 by the squeeze theorem. Alright, so taking the limits, what we got was that this one was equal to 0 and this one was equal to negative I pi, and we changed this into x. Oh, I think this should be x. Anyway, yep. So we apply the limits of r and epsilon. Basically, we've just rearranged the equation here. So we move this I pi to the other side as well. How we've got I pi. And now we can just combine the integrals, and it's a similar form to sine x. So we can substitute that in here, rearrange, and we can take out the 2i there, and that means that the left hand side of the equation is equal to this, which is equal to I pi. So we rearrange and we get the original integral that we're trying to calculate is equal to pi over 2. So just to summarize what we did, basically we found the contour. Sorry, let me go back. We found the contour that we wanted such that it would fit this and it would not include 0. We split it up into 4 separate parts. We looked at the behavior as the limits took place, and what we ended up with, also we used Cauchy-Gaussat to equate it to 0 as it was closed. Rearranged our equation to find the original integral here. Alright, so I'll just quickly finish these ones as well. So we've got the Cauchy's integral formula. So suppose that omega is a simply connected domain, f is holomorphic on omega. This is simply a simple closed contour in omega, and w is in this. Then we have the integral formula here. This form is probably easier. Basically we have this w here, the function z, and then we substitute in the value of w and multiply by 2 pi I. So our first example is a little bit different to the form that we were looking at. So what we do is we actually use partial fractions to split it up and such that it's got like one term on the denominator. So there we go, partial fractions, split up the integral, and now we can apply Cauchy's integral formula. So Cauchy's integral formula, we see that the f of z is going to be the top here, which is e to the z. W is going to be 2 here and negative 2 here. Therefore, the integral, once we substitute it in, is 2 pi I over 4, because of 4 here from the partial fractions, and we substituted in the w into f of z, and we get e to the 2 minus e to the negative 2. So it's important to note that when you're applying this, basically these values of w have to be within like the contour that you're working with. So in this case we could apply it because the contour that we're working with is a circle, that's a circle of radius 3, and these values of 2 and negative 2 are going to be inside, so we can apply the integral formula. Next we have the generalized integral formula, which is very similar, except we've got now a power on the bottom. So easy to remember, it's pretty similar to the previous one. We've got n factorial here. We can see that in our previous case, the original integral formula is the case where n is equal to 0. So if we have n as 0 here, so it's just 1 here, n factorial is 1, and this is the nth derivative. So in our case of the 0th term, it was just the function if we didn't derive it. But yeah, so now you need to derive it n times based on this power here and divide by n factorial. Alright, so applying this, once again we've got our function f of z on the top, which we need to substitute, or in this case we need to derive it twice because n is 2. We'll substitute in w, so we can observe that our w is going to be this value here, which is pi, sorry, this value pi, and n is equal to 2 because remember in the formula it's n plus 1 on the bottom here. Alright, so what we do is we just substitute in the formula 2 pi I over n factorial, and we calculate the second derivative of f, which is going to be 2. Alright, so because it's 2, then this is 2, but this cancels out with the 2 factorial, therefore the value of this is going to be 2 pi I. And once again, as I was saying before, you can apply this when the w here is inside this contour here, which is true because once again we've got a circle of radius 4 and we've got pi here, which is inside the contour, so we can apply it. Alright, so next example will show that if f is an entire function such that the modulus of f of z is less than the modulus of z to the k, then f is a polynomial of degree at most k. Okay, so basically if f is a polynomial of degree at most k, then that means if we have any derivatives larger than that, then the derivative will just be equal to 0. Alright, so applying the Cauchy's generalized integral formula here. Yeah, here we're just choosing the contour to be equal to r, a circle is easy, and we use the circle inequality here because we're going to be looking at this bottom here. So this is greater than that, and we take both sides to the k plus n plus 1, and of course r is here, so we can substitute that in, and we'll take the reciprocal of both sides, and now we can consider that f of, from here, from the question, f of z is going to be less than the modulus of z to the k, so this will satisfy here, and then we can also substitute in r again. And now from the ML lemma, so we just multiplied this by n factorial over 2 pi I. And r is, now that we have this, r is arbitrary and n is a positive integer as defined before. We can have r approaches infinity, which gets us this term which we were looking for. This is by the generalized integral formula. This left side is equal to this middle part. And this is r approaches infinity will be equal to 0. Less than or equal to 0, because what will happen is we have r to the k plus 1 on top, and then we have on the bottom r to the k plus 1 plus n, where n is a positive integer, so this will evaluate to 0. Hence, we say that this derivative, the k plus nth derivative, is equal to 0, and that will satisfy our requirement here. Yeah, just rewritten that here. Okay, so almost finished with the Louisville and Moreira's theorem. So first, suppose that f is bounded and entire, then f is constant. That's what it means. And we also have suppose that omega is a domain, f is continuous on omega, and the integral of f of z with respect to z is equal to 0 for every closed contour, then f is holomorphic. So this is the reversal of the Cauchy-Gaussat. Before we had, it was required to be holomorphic, and then we could apply this to equal 0, but now we're just saying the reverse. If it is equal to 0, then that means that f is holomorphic. Alright, we've got an example, last example here. Find all entire functions f of z such that the size of f of z is less than or equal to the size of cosine of z. So we'll just consider a function here. This would satisfy our equation. So this is going to be less than this, which means it's going to be, the size of this is going to be less than or equal to 1. We can make g entire by essentially removing, we don't want to deal with, it's not entire unless we deal with this denominator equaling 0. So what we do is we'll just set a limit here if the cosine of this is equal to 0. And since g of z is bounded, g of z is equal to c for some c by Louisville's theorem. Hence, by definition of g, f of z is equal to c cosine z. So basically we've written g of z as c here with this condition here. Multiply both sides by cosine, and we're just left with f of z is equal to c multiplied by cosine z. Thus, we can say that, substitute in f of z here, divide both sides by cosine of z, which means we get our c here is less than or equal to 1, which is what we desired. Alright, so that's it for this part. I believe the next part is on Saturday at the same time, 12 to 2 p.m. And yeah, just say good luck and thank you for watching. See you.